right. I'm sorry that I can't be here today. I hope that if you're watching this video that it kind of helps make some sense out of the notes that I have posted in Schoology. Be sure that you've got a calculator. Today we're going to do quite a bit in there. So this chapter is only 3 lessons long. This is the middle lesson, 8.2. We're going to continue with the concept. The whole chapter is about confidence intervals. Today you're going to learn actually how to calculate those, whereas in 8.1 it was given to you and you interpreted it. So you'll calculate confidence intervals for a proportion, and then I'm going to teach you about something called the 4-step process, which is going to be really important for your free response questions. Let's review something from kind of a long time ago. Hopefully this is something that's easy for you. In a standard normal distribution, standard meaning the mean is 0 and the standard deviation is 1, what percent of the values are within 2 standard deviations of the mean? So if you want to draw a little picture for yourself, we are dealing with a standard normal distribution, which again means the mean is 0 and the standard deviation is 1. And we're being asked what percent of values are within 2 standard deviations of the mean. And this goes back to something called the empirical rule, or the 68, 95, 99.7 rule. And the 68, 95, 99.7 rule kind of gives it away. It says that 95% of values are within 2 standard deviations of the mean. So about 95% of values are within 2 standard deviations of the mean. About 2. Today we're going to learn how to be a little bit more precise with that. So let's talk about part B. This is going to become a really important skill for you to have. When you're given different confidence levels, the different percentages in your word problem, you're going to be having to calculate essentially what we did up here, but we can't use the empirical rule because we don't know. Like, it's called the 68, 95, 99.7 rule. There's no 90% in there. So this is asking the same style of question in a standard normal curve. 90% of the area lies between what 2 values? 90%. So here's the deal. I can kind of estimate it using the empirical rule. I know that 90 is somewhere between, it's going to be probably between 1 and 2 standard deviations of the mean, if I'm just using estimation skills here. But I want to know what these exact values are, because that's the question that's being asked. It's saying 90% of the values are between what and what? Or 0.9 of the area would be the proportion of the area is between those 2 values. So in this situation, where you're given a percentage or a proportion and you're having to find the values, that's when we use our inverse norm function in the calculator. Inverse norm. And when you're asked for inverse norm, it's going to ask for the area, the mean, and the standard deviation. We know mean and standard deviation are 0 and 1. Now, inverse norm, for the area, you always need to be typing in the area to the left of the critical value of interest. And since this has some symmetry to it, if I can find this question mark, this negative value, then I know this will just be the positive version of that value. So go to your calculator and go to second vars, inverse norm, and the area to the left of this critical value, well, if I take 90% out of the middle, then I've got 10% left for each tail. So that means there would be only 5% in this tail. So the area I'm going to type in, or the proportion of the area I'm going to type in, is 0.05. And let's take this out to 3 decimal places. So this question mark, this value right here, is negative 1.645. About 90% of the area lies between negative 1.645, and I said because of the symmetry here, we know that this is positive 1.645. And another way of saying that is, and I'm going to show you this in just a second, z, because this is a z-score, a z-value essentially on a standard normal curve. The z-value that we just found would be positive or negative 1.645. And what you just found is very, very important. It's called a critical value. When you find that z-value, you found something called the critical value, and it's important in the lesson later today because on your yellow formula sheet, when you are calculating a confidence interval, it says that you're going to take the statistic and you're going to add or subtract what's called the critical value multiplied by the standard error. Now, the standard error of the statistic, those formulas are on the back of your sheet for you. So you'll be able to have those formulas at hand. The critical value is something that you're going to have to remember how to find. It's finding that z-value for your confidence level, the percentage that's given in the problem. All right, now the next question here says, so what's it called, what's the name of the procedure we use when calculating a confidence interval for a proportion? This is important when you're writing the 4-step process, and I'll show you this later. You need to know what test it is that you're performing so that you can label that. And what we're doing is it's called, when you're creating a confidence interval for a proportion, it's called a one sample z interval for population proportion. One sample z interval. And then just as a recap, you have to make sure that these conditions are met. And so you need to make sure that somewhere in the paragraph it explicitly says that the data come from a random sample. The 10% rule says that when you're sampling without replacement, that the sample size must be less than 10% of the population. And then the large count condition, which again, you're always going to use to assess the shape, the normality. You use large counts anytime you're dealing with a problem about proportions. And that's when you're going to plug into n times p hat and n times 1 minus p hat are greater than or equal to 10. Now, one thing I haven't mentioned yet, this is very, very important, is that when you calculate these values right here, you kind of notice that they add up to be the sample size. The values that you get for these two parts add up to be the sample size. Well, if you think about it, what you're finding there is the observed number of successes, that's going to be n times p hat, and the number of failures, which is going to be 1 minus p hat times n. That's why when you add those together, you get your sample size. So you get successes and failures here. And that'll be important later if you kind of want a shortcut to use in the calculator. You have to know the number of successes that you have. We have to use p hat here. If you've noticed, our formulas used to say n times p, and now they say p hat. But remember, in this chapter, we're going to be given the statistic, and we're going to be figuring out the parameters. So we're given p hat, so that's what we'll plug into the formulas there. So the general formula for creating a confidence interval is the one that I showed you on your yellow sheet just a second ago. We're just going to copy this down. Confidence interval is going to be a statistic plus or minus critical value times the standard error of the statistic. And then we'll just kind of label what those things are. And I'm going to abbreviate confidence interval for CI. So we're going to take the statistic and we're going to add or subtract the critical value, which you practiced finding at the top of your page there in that part B, times the standard error of the statistic. And I just want you to note to yourself that the formula for this standard error of the statistic that we're talking about, the formula for that is on the back of your chart. Clearly labeled. Now, the statistic that we're talking about today is going to be p-hat. Because we're talking about proportions of samples. And then the critical value is called Z. Usually there's a little asterisk by it. That doesn't mean anything. It's just to denote what we did up there in part B, finding that critical value. And so, what two factors determine the margin of error? Well, let's revisit our 8.1 definition of what a confidence interval was really quickly. In our last set of notes, we wrote that a confidence interval is just the point estimate plus or minus the margin of error. Right? Because we said in a confidence interval, you've got your point estimate in the middle, and then your margin of error determines the width of that confidence interval. So those two things kind of make up the confidence interval. Well, now with this formula, you can see that the margin of error is made up of the critical value and the standard error of the statistic. So I have that written down in the notes on Schoology, but I'm just kind of saying it out loud here if you want to jot it down. The margin of error is made up of the critical value and the standard error of the statistic. That's the question that it was asking here. All right, go ahead and turn the page. And here we finally get to figure out where on the formula sheet we can see the standard error of p-hat and what it measures. Like, what are we finding? So on the back of your formula chart, here's the standard error formula for a population for p-hat that we're calculating. And the standard error essentially looks, in this case, identical to the standard deviation of the sampling distribution for p-hat. So what's the difference? Well, if you'll notice, because we have information that we take, pull data and get us from a sample, we're using p-hat instead of the population proportion. And I will tell you just a second, kind of this estimates this value over here using one single sample. So we're going to write all of that down. So the standard error of p-hat on the back of the formula chart says standard error of p-hat equals, and it's the giant square root of basically the number of successes, the p-hat times 1 minus p-hat, all divided by n. Here's what that tells you. Once you crunch the numbers and you get some kind of a decimal value for that, it tells you how far p-hat typically varies from p. It tells you how far the statistic typically varies from the parameter, the population proportion. And I told you that what we're going to write down is kind of like what is this measuring and why is it different than the standard deviation. It's an estimate, and it says this actually on your formula chart down there in the fine print. That standard error is just a measurement of variability. It's an estimate of the standard deviation of the sampling distribution of p-hat. But it's an estimate because we're using only one sample to crunch the numbers, using only one sample from the population. The formula for this, you go into this knowing the population proportion. The standard error helps us calculate, estimate that with only one sample. So what is a critical value, that Z value that we find, and how do you calculate it? By definition, what a critical value is it's just a multiplier. in the formula it says critical value times the standard error. It's a multiplier that makes the margin of error large enough to give a specific amount of confidence that the interval contains the value of a parameter. Don't worry too much about that definition there. Find the critical value for a 95% confidence level. Okay, now, here's what I want you to understand. The very first thing that we did in our notes, we said that about 95% of the values are within 2 standard deviations of the mean. But this time I want to be more accurate. So the critical value for 95% is not 2, it's really close to 2. But let's use this skill, let's use what we did on this problem to calculate the critical value for a 95% confidence level. So it's really close to 2, but if we use our inverse norm, and again, it's going to want area. Think about this. If I have 100% of the area under the curve, I take out 95%, that leaves 5% split between the two tails. I'm going to draw a teeny tiny little picture here. So the area to the left of the critical value over here, and this will just be the positive version of that, the percent that's remaining in here is really just 2.5%. So the area that we'll type in is 0.025. And then we're talking about a standard normal curve, so mean is 0 and standard deviation is 1. Let's do that really quickly and come up with the critical value for a 95% confidence interval. Here's the really cool thing while you're finding this on your calculator. This is never going to change. So the z-value, the critical value for a 95% confidence interval will always, always, always be positive negative 1.96. And we are technically taking it out to that third decimal place, but the 9 rounds the 9 and the 9 rounds the 5. So positive negative 1.96. That's a skill you'll need to have depending on your word problem, what percent the confidence level is. You'll have to use inverse norm, or if you're a memorizer, I think it's a good idea to memorize 90, 95, and 99% confidence levels to memorize the critical value for those. A lot of AP students do that. All right, what's the specific formula for calculating a confidence interval for a population proportion? Is it on the formula sheet? Kind of. Because it's that one that says statistic, let's write confidence interval for population proportion. It's kind of on there because it says statistic plus or minus critical value times standard error. The statistic is p-hat plus or minus the critical value times the standard error of the statistic, which is technically embedded in your formula sheet, which we practiced, or I showed you at the top of the page. So you won't find this exact formula on your formula sheet. You're going to have to piece it together by knowing that the statistic we're talking about, or the statistic that's given, is p-hat. Critical value is that z, those z values up there, and the standard error for population proportion is on the back of your formula sheet. All right, I love this part right here. I would highlight this, circle it, make sure that you, like, this sums everything up for those of you that have been struggling on all these different conditions and like what happens if they're violated. So the random condition helps ensure that p-hat is unbiased. So as long as you've got a random sample, then that ensures that your statistic is an unbiased estimate. The large counts condition tells you about the shape. It allows us to use that normal curve, to use that inverse norm feature in the calculator to find the critical value. And the 10% condition allows us to use the standard error formula, even sampling without replacement. So that's the value of those. That's why we take a second and we find those. All right, let's try applying what we've learned so far. What proportion of U.S. adults contribute to crowdfunding campaigns like GoFundMe and a random sample? So the sample size is 1,535. it was gathered randomly, U.S. adults, 487 reported that they give to crowdfunding campaign in a typical year. A, verify that the conditions for calculating a competence interval for P are met. So let's just take that one little bit at a time. And it really doesn't matter what you start with. You want to check that the sample is gathered at random, and it really does say random sample in the problem. So you're showing the AP grader, yes, the random condition has been met. 10% condition. The 10% condition says that the sample size has to be less than 10% of the population. Well, 1,535 U.S. adults is less than 10% of all U.S. adults. Again, if you're in doubt, just stick a 0 on that. There are more than 15,350 U.S. adults. So that's checked. And then lastly, let's check for the large counts, which will tell us our number of successes and failures. And it should add up to that 1,535. So we're going to take sample size times p-hat, check that it's greater than or equal to 10, and the sample size times 1 minus p-hat, check that it's greater than or equal to 10. And the really cool thing is, if you're really understanding that these values add up to be the sample size, you can just find one of them. Find the successes, and then subtract that from the sample size to get your failures. It's always going to work that way, and that's what's really cool about it. So the sample size is 1535, and I'm going to multiply that by, okay, now wait a minute. It says 487 said that they gave to a crowdfunding campaign. That means I need to take a second out to the side, and you've got to understand that it didn't give you p-hat. You need to find, okay, 487 out of everybody in the sample said that they gave to crowdfunding. So that's going to be 487 divided by 1535. That's going to be p-hat. And let's go ahead and take it out to 3 decimal places, 0.317. So they gave us p-hat in kind of a roundabout way. So in the calculator, I'm going to take my sample size, 1535, times that 0.317. And I'm going to get 486.6. So let's round that to the nearest integer, and let's say that we have 487 successes, which is certainly larger than 10. And then what I was showing you, what I meant earlier, was if you take that sample size and just subtract off the number of successes, the people that did say that they give to crowdfunding, then this many people said that they don't. So 1,048, and that's also certainly larger than 10. So all the conditions have been met. Part B says calculate a 90% confidence interval for P. Alright, so to calculate the confidence interval, we need to use the formula that says confidence interval is going to be p-hat plus or minus z times p-hat times 1 minus p-hat over in the square root of all of that. And I'm just going to work horizontally. And so p-hat was that 0.317 plus or minus. Our critical value for a 90% confidence level is always going to be, we did it on page 1, if you want to cheat a little bit, it's always going to be 1.645. So for those of you that like to memorize, that's what I was saying. 1.645 times the square root of 0.317. And I'm going to go ahead and just do 1 minus 0.317 here so that I know 0.683 goes in the parentheses there. That's that 1 minus p-hat. That's what I put right there. 1 minus 0.317. all divided by the sample size. Okay. Putting this in the calculator could be tedious because you have to do both the minus part and then you have to recalculate it with the addition. So you have to do the subtraction and the addition. The way that I'm going to choose to write this is in the form of, it almost looks like an ordered pair, that kind of interval notation, where I put the the confidence interval's lowest value, comma, highest value. So in the calculator, this is going to be a nice little shortcut for you. Let's put 0.317. Let's do the subtraction first so that we get our smaller value first. And then 1.645 times the square root of alpha y equals enter will allow me to get that fraction, 0.317 times 0.683 on the top over the sample size. So it looks just like I have it on the paper. Okay, I'm going to go ahead and hit enter. And here is the lower value of my confidence interval, 0.297. Okay, listen really closely so that you don't have to go through and do that all over again. If you will arrow up and highlight that previous entry, the only thing that's going to change, hit your left arrow until you get back to the subtraction sign and just change it to a plus sign. And then hit enter, and then really quickly and efficiently you can get your upper value. So 0.337. And then let's take our skills from our notes last time and interpret. What is that telling us again? We did all of that work. We had to check the conditions to be able to find it. And what did we just find? We found that we are 90% confident. You're always going to plug in the confidence level given. We are 90% confident that the interval from 0.297 to 0.337 captures the true, and then I always have to kind of glance back and ask myself, what was this problem about? What was the parameter? What was I gathering about the population? And if I glance back up here, it's the proportion of U.S. adults who would give to a crowdfunding campaign. Now listen really closely. It's not the proportion of adults who said that they did give to a crowdfunding campaign. And those are the tedious little things that AP graders will mark off for. We already know how many said that they did give. So when you're wording it down here, be sure you understand it captures the true proportion of U.S. adults who would give to crowdfunding campaigns. That's what we just found. All right, turn the page. There's really not going to be anything new that we look at right here. We're just going to put it all together in something called the 4-step process. What are the 4 steps required in an FRQ when you see the instructions? Now, I see some of you heading into this next test not reading closely and understanding. When it just says to construct and interpret, you might think, oh, I can jump right to the formula, I can calculate it, and then I can interpret it. But you're going to be missing some pieces, okay? The 4-step process on a free response, when you're asked to construct and interpret a confidence interval, you need to state what you're going to do. I'll show you what that looks like. That's the first step, is to state what the task is. And then you're going to show that you're planning on it, which means you're going to check all the conditions have been met. That's going to go in the plan piece, and you're going to write what the test is called that you're performing. And then you're going to do, that's where you actually calculate, you crunch the numbers, use the formula, figure out your confidence interval, and then conclude is where you interpret. State, plan, do, conclude. And we're going to practice that right now so you can see exactly what it looks like. Would you favor or oppose making Washington, D.C. a state? That's the question. The Gallup polling organization asked a random sample of 1,018 U.S. adults. If the selected adults, 29% said that they favor. So there's our statistic. 0.29 is the proportion in the sample who said that they favor making D.C. a state. Construct and interpret a 90% confidence interval for the proportion of all adults in the U.S. who say they favor making D.C. a state. All right. So let's follow these 4 steps. The first thing we're going to do is state, and you can always set it up like this, state. What we're doing here, we're stating what we're doing is we are performing a 90%, or calculating, excuse me, a 90% confidence interval for, and here's where you're going to define what your variables mean. A 90% confidence interval for P is going to represent the parameter, which is the proportion of U.S. adults who would say not who did say, but who would say they favor making D.C. a state. So we just stated what it is we're going to do. Plan. You're going to check that the conditions have been met, but you need to talk about what type of test it is that you're performing. Now, technically what you're performing here is a 1 sample. This is on page 1 of the notes. Z interval for P. We've already defined right up here what P is. So 1 sample Z interval for P. Here we go. We're going to test for the random 10% and large counts condition here in the plan step. Random. I'm just going to quote what it says up there in the paragraph. It does say random sample. Check. 10%. Again, they asked 1,018 U.S. adults, so I'm just going to say 1,018 is less than 10% of all U.S. adults. Check. Large counts. This lets me know that it is got that normal shape, so I can use the inverse norm. It also tells me the number of successes and failures. So n times p hat and n times 1 minus p hat must be greater than or equal to 10. The number grabbed in my calculator in the sample was 1,018 times the statistic, which this time we don't have to calculate it. It said 29%, so 0.29 is p hat. And I get, we can round that to 295 successes. 295 people said that they would be in favor of DC becoming a state. And then I'm just going to take the sample size, 1,018, and subtract off those people. And 723, we could consider these fails in a binomial setting, but those will add together to be your sample size. Those are both greater than or equal to 10, which means our plan step is now complete, and we're going to move on to the do, which is actually figuring out what the confidence interval is. So we're going to calculate it now. So confidence interval is going to be p hat plus or minus the z value. There's our old friend 90%. So if you're a memorizer, you don't have to pause and do the inverse norm business. If you need to do that really quickly, if you like to do it each time just to be extra thorough, 90% taken out of the middle leaves 10% on each side, on both sides. That's 5% on one side. So you can quickly figure out, again, take it out to the third decimal place, that the critical value here is positive negative 1.645 times the square root of p hat times 1 minus p hat all over the sample size. And I'm just double checking this value here. Okay. Everything looks good. I'm going to type this in my calculator with the subtract symbol, and then I'm just going to go back and edit and change it out for a positive symbol. And I get 0.267. And then we'll go back and left arrow, change that out for a plus, all the way up to 0.313. That's the do component. It's actually crunching the numbers. And lastly, we're just going to interpret that with our sentence frame for the conclude piece. All right, we are 90% confident that the interval from 0.267 to 0.313 captures. You can always just glance back up at the top of your page. Like what do they want me to find? The proportion of U.S. adults who would say that they favor making D.C. a state. Captures the true proportion of U.S. adults who would say, remember, that's really important, not who did say, but who would say that they favor making D.C. a state. And that is the four-step process. Yes, it is tedious. If you want to get full credit on an FRQ that asks you to construct and interpret, I'm being very clear, this is how I'm going to grade my tests as well. You must have all of those components. You can't just crunch the numbers and interpret it. And that's what's deceiving about the instructions, is it seems like you're just supposed to do those two parts. But you can't even calculate it if you haven't checked the conditions have been met. All right, so a burning question that a lot of people have is, there are all these conditions that we have to check. Well, what happens if they're violated? Like, I start to check them and like it doesn't say that the sample was random. What if I notice that there's some bias in the way that the sample was gathered? Well, you can't do anything. In that case, as a statistician, if the random condition is violated, you would just have to start the process over and make sure that you gathered a random sample. So you can almost be positive as an AP student in a free response question that will be met. Multiple choice, they might kind of make you call them on it where the sample wasn't drawn at random. If the 10% rule is violated, and we touched on this in the last chapter, that just means our standard error is going to be overestimated. It's going to show that it's larger than it should be. So our success rate will be higher than our confidence level. And if the large counts condition is violated, our assumption that the distribution of p-hat is normal is wrong, and so our success rate is going to be less than the confidence level. I'm going to show you how you can do this in the calculator. I really just kind of don't recommend it. I'm all about giving you guys shortcuts, but this in and of itself is not difficult to do, to pick out those pieces from the paragraph, plug them in, and get your answer. The calculator can do this red part for you, but I really don't think it's worth learning an extra thing. I am going to show you right now, though, if you're interested, how the calculator can come up with the confidence interval for you. Is it okay to use it? Yes, you can. Here's what you're going to do. You're going to go to Stat, Tests, and you're going to be sure you pick the one that says 1 crop z int interval. And it's going to ask you for three things. It's going to ask you for an x value, an n value, and a c level. N is always going to be sample size. It always has stood for sample size. You could probably figure out that C level is your confidence level that's given in the problem. Here's where people this is why learning this extra step can be frustrating for some. X specifically is the number of successes, and it has to be an integer. You can't put, like up here when we got, I don't remember what it was, like 295.2, you would have to put the 295 in for your number of successes. So that number of successes can be found by using this little formula here, n times p hat. But that's the value that you must put in for x. It's not asking for a p hat that's given in the problem. So just be sure that you have to use the formula anyway, like you're gonna have to show this work. So that's what's, to me, kind of seems like it's just extra fluff to find this part in the calculator when technically you can just type all of this in. But you need to show that you're using the formula with numbers substituted in to get full credit. It might be kind of a good thing for those of you that like to be very thorough, to double check. Just be sure you don't give both answers if the one in the calculator is slightly different because of rounding. Give one or the other. They're not going to count off for little rounding errors. And then, again, just make sure that whatever you type in for x is an integer. It can't be a decimal value. Try the example above in your calculator to practice and verify your work. So this is cool. We're just going to make sure that you understand how the calculator can give us this really quickly. So here we go. Go to Stat, Tests. Be careful that you go all the way down to one prop z int. It's not this one prop z test. And it's A on the menu down there. Now, because we already did the work up here, the number of successes I'm going to type in is 295. And the sample size is 1018, and the confidence level was 90%. Just enter that in as a proportion and a decimal 0.9. Again, this can seem like it's just extra stuff for you to do, and here's what the calculator gives us is the confidence interval. 0.2664 to 0.31317. 2664 all the way up to 0.31317. Now that's almost exactly what we calculated by hand up there. So if this seems like just extra stuff for you to do, don't worry about it. If you think that this is a good way to check your work, then that's how I would utilize that little trick right there. All right, last page of the notes. Suppose you want to construct a 99% confidence interval for a proportion of all students at school who have a driver's license. What sample size would you need? So we're going to flip it, and you're going to be solving for n sample size to guarantee that your margin of error is at most 0.08. So remember, your margin of error is the critical value. Margin of error is going to be your critical value times the standard error. Lots of vocabulary words. That's the margin, and I guess I should put MOE for margin of error to be consistent with how we've done it in the notes before. Okay. So I want to make sure that the margin error is at most 0.08. So basically, I'm going to take this right here, and I want to make sure that it's less than or equal to 0.08. So let's plug in what we do know. We can figure out the critical value for 99% confidence interval. We haven't done that yet. So let's pause, use our inverse norm, think about it really quickly. I'm going to draw a teeny tiny little picture. This always helps me. If I have 99% taken out of the middle, that leaves 1% on either side. So that just leaves half of a percent in that left-hand tail. Be careful, that means 0.005 is going to be the area to the left of the tail. For those of you who like to memorize, this will always be the critical value for a 99% confidence interval. So positive, negative 2.576. And then it says figure out what sample size you would need. So we know that sample size is what we're going to be solving for essentially. Here's the issue. Nowhere in this problem did it give me some kind of statistic that said, hey, we pulled a random sample of students and found this percentage had a driver's license. So we're stuck, and here's why. We don't know p-hat. And if you have more than one variable here, you're not going to be able to solve. So that's kind of where we're stuck for now. We will finish this out at the bottom of the page because I'm going to give you a little insight of what happens if you're not given the statistic in the problem. What do you plug in for p-hat? All right, this is probably should have come first at the top of the page, but the formula for the margin of error, that's what we wrote at the top, for confidence interval is z times p-hat 1 minus p-hat over n, the square root of that. Is it on your formula sheet? Not really. It just tells you, again, the confidence interval is the critical value times the standard error. Those two parts make up the margin of error. So you've got to just kind of deduce that. So what do we do? How do you choose a value for p-hat if it doesn't give you one? And I'm basically going to tell you the long and the short of it is you're just going to use 0.5. So you're either going to use a value from a previous study or a pilot study. That sounds really weird, but it'll actually say those words in the word problem. It'll say, you know, a pilot study showed that this percentage of students in the sample size of blank had, or this percentage of students had a driver's license. So you could plug that in for p-hat. Or it might say in a previous study it was found that this percentage of students had a driver's license. So if it uses that wording, that's the value for p-hat you're going to use. If it doesn't give you anything, like in our problem, you're going to use 0.5. And the reason is it just because anything smaller than that would just give you a smaller margin of error. And so we want to just kind of make sure we're hanging out somewhere in the middle to be fair. So just use 0.5. All right, that means that we can finish the problem at the top of the page. It's going to require some algebra skills. We've got 2.576 times the square root of p-hat. Since it didn't give us one, we're always going to plug in 0.5 when we're not given a value for p-hat, unless it says there's a previous study or pilot study and it gives us a proportion for that, over n. We're figuring out what sample size we would need to have a margin of error of at most, which means less than or equal to 0.08. So now we are just going to do some algebra. The first thing I'm going to do is divide both sides by 2.576. Think about what that would result in, okay? Now this is gone. And now I've got the square root over here. So to get rid of the square root, I would have to square both sides. I'd get rid of the square root symbol. And I'm going to go ahead and calculate 0.5 times 0.5. So here's kind of where I'm sitting now. I'm going to have to multiply both sides by n to get the n out of the denominator. Now n is sitting nice and happy over here in the numerator, and I'm going to have to divide by this fraction that's being squared. It's really important not to round until the very end of the problem if you can help it. So I've got this 0.25. I'm going to now divide by this giant fraction 0.08 over 2.576 squared to get my value of n. Let's do this and kind of see what we get. And the last component is making sure you're really careful on how you round. I'm just going to type it in as exactly as it is on the paper. And I get messed up somewhere. Let me pause this and figure out what I did wrong. Well, apparently I didn't mess up here. I messed up previously, so if you're copying the notes on Schoology and not watching the video, you're going to have the incorrect information. This is going to be 259.21. Well, we're talking about people. So we're trying to figure out how many people need to be in my sample. And so I want n to be greater than or equal to this number. So I'm going to word it like this. I need at least 260 people in my sample, because if I rounded down to 259, that wouldn't quite cut it. So at least 200, or you could put a sample size of at least 260 is needed. To ensure a margin of error of no more than 0.08. Whew, and that finally does it.